Irene Mays Pilar. Welcome to the Waves and Optics class. This day, I'm gonna show you how to make my DIY fluorescent resonance tube experiment. This day, I'm going to discuss first the theory of my DIY fluorescent resonance tube. According to this theory, resonance is observed when at specific frequency the sound produced by an object seems to be louder and amplified. This phenomenon can also be observed in tubes, or what we can call as air columns. When the two waves of equal wavelength and amplitude propagating in opposite directions superimpose on each other, then the interference occurs and the resultant wave is called the standing wave. In standing wave, the particles of the medium at certain points do not oscillate. These points are called nodes. At a certain points, the particles of the medium have a maximum amplitude of the oscillation called anti-nodes. In standing stationary waves, the distance between the two consecutive nodes or antinodes is the wavelength over 2, whereas the distance between a node and the successive antinodes is the wavelength over 4. In an air column, specifically a closed air column, it produces a standing wave that propagates across the end of the column. The closed end is constrained to be a node of the wave, and the open end is of course a antinode. This makes a fundamental mode such as the wavelength is 4 times the length of the air column. This constraints of the closed end prevents the column from producing the even harmonics. When the frequency of oscillation of the vibrating object is equal to the natural frequency of the system, then the resonance occurs. As shown in the figure 1, a speaker generates frequency. When the speaker is tipped over the open of the partial filled tube, then the sound waves propagating in the tube are rejected back from the surface of the water. A standing wave pattern is generated if the frequency of the speaker is equal to the natural frequency of the air column inside the tube. Then the node of the standing wave pattern is produced at the water surface inside the tube, and the antinode is produced near the open of the tube. In the theory, each air column has a specific frequency at which the sound is amplified. This phenomenon is what we call resonance frequency. In this experiment, we will know the resonant frequency of a closed tube at the different lengths. For the objectives, determine the resonant frequency of a closed tube with different lengths. Second, determine the range of the frequencies amplified by DIY's cell phone resonance tube. This time, I'm gonna show you how to make my DIY fluorescent resonance tube. For my materials that I'm going to use, which is the frequency generator through online, or I downloaded the apps on my cell phone. Then the cell phone with temperature at the frequency generator application also. Then I have a 1 meter transparent tube or recycled fluorescent bulb, reservoir, which is the recycled brown plastic around 5 inches length, ruler, marker, polyester, medical tube or hose pipe, which is 1.5 meter, cutter and scissors. So if you want to make a DIY fluorescent resonant tube, you can follow what I did in my procedure. this day, I have here the materials. This is my reservoir. Then this is my tube, which is made by the fluorescent lamp. Then this is our stand. So
I have downloaded the application in measuring the temperature. So we have a 20 degrees Celsius, the temperature inside the air column. I have also downloaded the application of frequency generator that we will going to use to measure the resonant frequency. So I have also here the frequency counter that we will use to measure the frequency or the resonance that produces by the air column.
for the first trial, so just listen and observe what happened to the level of water and the frequency or the resonant frequency. Today, I'm gonna show you first the 380 Hertz. So I'm going to use this audio frequency in 380 Hertz. Then, for the second trial, just observe what happened to the length of the level of water in the tube and also the resonant frequency. I'm going to adjust the hertz into 390. And the third trial, observe also the level of water. What will happen also for the resonant frequency. So this day, I'm gonna adjust my hertz into 400 and listen. Then, for the fourth trial,
Day I will add
observe what happened
10 hertz so that will make it a 410
the water, then the resonance also from the frequency. Observe what happened to the resonant frequency. Then for the fifth trial,
I will add it again.
Observe all.
10 hertz so that it will make
watch
it to 420
what will
hertz.
happen to the level of water and the resonant frequency that produces by the phone. Then for the sixth trial, observe what happened to the level of water and what happened to the resonant frequency when increases or decreases the level of water.
Hertz. Today I'm going to add 10 hertz again so that it will make it 430 hertz.
For the seventh trial, by lowering or rising the reservoir, as you can see that the level of water it
440 hertz
affects the resonant frequency. Then for the eighth trial, as you have observed that by decreasing the level of the water in the air column,
450
as well as the air column increases, so the resonant frequency decreases. After we did the 8 trials, so we have made the table so that it is easy for us to determine the difference between the length of the water level inside the air column and also the frequency as we measured in hertz. So in 20 degrees Celsius of the air column, as you can see that in our first trial, there's 86.36 centimeter, which is the length of water in the air column in centimeter. So the length of the air column, which is, we have a formula that length is equal to x minus y. Our x is the 100 centimeter of our total length of our tube, which is the fluorescent lamp, that minus the y of our length of water in the air column, and this come up with 13.64 centimeter. And the speed of the sound, which is 340 meter per second, and with that we have also calculated the resonant frequency with 85.75 hertz, and also we calculate also the wavelength that we have also here the formula that wavelength is equal to 4 times length. So in the first trial, we have the wavelength of 54.56 centimeter. So we have here the relationship between the resonance air column versus the resonance of frequency. We measured also the lowest and the highest frequency of our audio frequency using my cell phone. So I will be using this so that I can control the level of water while measuring the frequency on resonance of the
Tara. Measuring.
using the audio frequency of our phone. So, as you have observed that the lowest resonant frequency, there is a 172 Hertz. And the highest resonant frequency, there is
110 Hertz.
So as you can see, the data above, it shows that when the length of the air column increases, then the level of water decreases and the resonant frequency increases also. Otherwise, when the length of air column decreases, then the water level will increases and the resonant frequency decreases. Thus, the resonant tube becomes louder or softer depending on the water level within. Moreover, it serves to know the relationship between the length of the air column and the resonant frequency that is inversely proportional. It means that as the length of the air column increases, the resonant frequency decreases and vice versa. Using the online tone generator, which is used for the resonant frequency, and when you heard the loudest frequency if the air column is an appropriate size, and for the tube which is opened on the top as well as closed in the bottom. With that, we can fit an odd number of the quarter wavelength in that space of the resonant standing wave. So the measurement of the tube in centimeters, not perfectly the length of the tube. The tube has a effective length which is slightly longer depending on the width of the tube, so that it will introduce a little bit of error into the proceeding unless you explicitly can't account for a bit, but it differs to the phenomenon of the resonance frequency when lowering or raising the water reservoir. The difference between the resonance length is equal to the half of the sound's wavelength. So another factors in experiment that affected the air column is the temperature inside the air column. The temperature inside the air column stimulates the speed of the sound inside the air column, which affects the resonant frequency of the resonance air column. The equation being used is velocity is equal to 331 meter per second plus the 0.6 temperature, where the temperature is the temperature inside the air column, so the temperature is also the factor in the air column. Although temperature is one of the primal factors, the amount of the water mainly affected the resonant frequency, which affected the whole decreasing or increasing of length of our DIY fluorescent resonant tube. So for my cell phone resonance tube, when the length of the water level decreases, then the length of the resonance air column increases, as well as the lowest frequency that produced by the phone is 172 Hz, while the highest resonant frequency is 610 Hz, whereas the length of the water level increases. The length of the resonance air column decreases also. Yet, the changes of resonant frequency affects on the resonant tube of our phone, wherein it was classified as a mid-range type of resonant tube. This is because the resonant frequency of my cell phone resonance tube sits around 172 Hz to 610 Hz, and the mid-range type of tube sits around 200 Hz to 500 Hz. This means that my cell phone resonance tube is equal to the highest and lowest frequency of the mid-range type of resonance tube, making my cell phone resonance tube a mid-range. So based on the data and analysis that I have made, I can conclude that the appropriate size of the resonance tube of the air column and the length of an air column inside the resonance tube is the main factor affecting the resonant frequency in a tube. Moreover, as the length of the air column increases, it means it reduces the resonant frequency of the air column and vice versa. Furthermore, the length of the air column can be varied by the rising and lowering the tube. In continuing this process, it would reveal a whole series of shorter wavelength and the higher frequency sounds that resonate in the tube. At resonance, the amplitude of vibrating the open-end tube increases to a maximum. This is heard as the increase of sound intensity of the phone resonant frequency. Thus, a definite linear relationship between the length and the resonant frequency at an air column in a closed tube. This gives us an idea that by adjusting the length of the closed tube, we can create music by combining different types of frequency. The constraints of the closed end prevents the column from producing the even harmonics. The resonant frequencies of the air column depend upon the speed of the sound in air, as well as the length and the geometry of the air column. The longitudinal pressure waves reflect from either closed or open ends to set up standing wave pattern. It is important in visualization of these standing waves is the location of the nodes and antinodes of the pressure and the displacement for the air in the columns. That's all for today. Thank you for watching.